Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 54. And this problem asks us to determine what steps are needed to prepare our final product, phenylacetylene, from each of the following components. So we have A being this phenylic dihalide group here, B and C. So let's start with A. So we know that we are trying to gain a triple bond between these two carbons. We need to reduce the degree of saturation. We know we have two halides, which are good leaving groups, and we have two protons here as well. So what we can do here is, we know that if you take away this proton, then these two electrons can potentially make a new pi bond here. When you make a bond, you break a bond, so then we will kick off one of the bromines because bromines are very good leaving groups. So for example, if I were to use something like sodium hydride, which is H minus, or even sodium amide, which is NH2 minus, these can act as nucleophiles, being with lone pair electrons to pick up this proton making a bond. You make a bond, you break a bond, and then you made a new bond, and you make a bond, you break a bond, so this bromine will come off. And if you do this with two equivalents, then after the first one, you'll get this product. After the first equivalent, you'll get this product. And after there's still a proton here, so then after the second product, you will get your final product of interest. Like this. So now we have only one leaving group, bromine, in B, but it's on a secondary carbon, not on the terminal carbon. So these CH3 protons are not as acidic, so we can't actually do that same method here. But what we can do is use an even stronger base to make a alkene bond here. So if I use a strong, bulky base that doesn't do any like SN2 mechanism, because there might be an SN1 or SN2 mechanism that might be possible at this electrophilic carbon. So we need to add a very big and bulky base so it only acts as a base and not as a nucleophile. So a non-nucleophilic base such as potassium tert butoxide, it's very, very bulky. So it just acts as a base and not a nucleophile. So we know that you can pick up one of these acidic protons, making a bond. You make a bond, you break a bond, you form a new pi bond here, making a bond. When you make a bond, you break a bond, so your bromine will fall off. Now you have an alkene, but we need an alkyne. So what can we do? Well, we can add some bromines here. So if I were to add diatomic bromine, just like this, we know that the pi bond will act as a nucleophile going through the least bulky sterically hindered carbon to make a new bond. And then you would get your carbocation intermediate on your secondary stabilized carbon and a bromide ion that can now act as your nucleophile to form this transition of your halides. And then you can use a base like this, two equivalents or even excess base. So I can just add excess NH2 minus to rip off these acidic protons to form one pi bond and then the second equivalent. So I use two equivalents. Second equivalent will take this one, and then you'll form your final product. And you form your final product here. So now we start with something similar, but we have a very bad leaving group. So how can we make this bad leaving group into a good leaving group? Well, we can add some sort of like acidic water. So I add H3O plus. I know that this nucleophilic oxygen will pick up this proton, making this protonated water species. This is H2. It was positive charge on oxygen. So water likes to be neutral, doesn't like to be protonated. And also when we protonate this alcohol to water, we form the conjugate base of our reagent, H3O+, which is just going to be our water. So there will be some sort of equilibrium between H2O and H3O+. So we know that this water wants to fall off, but in order to fall off, it can spontaneously fall off to create a primary carbocation, but that's not really stabilized. So we know that in order to maintain this equilibrium between H3O+ and H2O, H2O will go back to H3O by picking up this proton, making a bond. You make a bond, you break a bond, you form a new pi bond, making a bond. And when you make a bond, you break off and kick off this water to neutralize everything and reform our acid catalyst. So remember, you always need to reform your acid catalyst or any basic catalyst or any catalyst of doesn't matter if it's acidic or basic when you're doing an acid catalyzed mechanism. So we form our water that falls off plus our H3O plus. We reform our acid catalyst. And now we have an alkene, which we can then follow the exact same steps in B to get our alkyne. Whoops, I always remember to count your carbons. And then 2 equivalents or excess NH2 minus to get your alkyne.